All right, so we're going to be talking about Pascal's Triangle, and as I said, like in the little comment on the page, Pascal's Triangle is one of my absolute favorite mathematical things that I learned, and I don't remember when I learned it. I know I knew it by the time I was in elementary school, in middle school, because I used to draw it on tables with my eraser, and so I wasn't really drawing on the table, but let me just explain it. It's pretty straightforward. Pascal's Triangles is basically, you start with 3 ones on the top, set up in a triangle format, and then you always put ones at the beginning and the end of the next row, and you get the terms by adding these together. So 1 plus 1 is 2. So my next row is 1, 3, 3, 1, because 1 plus 2, 2 plus 1, and so on. So 1, 4, 6, 4, 1. And we just build it out as far and long as we need to. There are a lot of amazing patterns embedded in Pascal's Triangle. One thing to keep in mind as we go down, the top row has 1, then 2, then 3, then 4, then 5, then 6, and it always adds. We call this the 0 row. So this is the 0 row, and then first row, second row, third row, fourth row, fifth row because of the 5. That's how you keep track of what row you're on. And it's what matters in the long run. So one of the things we can do with Pascal, and again, you can build this out as long as you want. I used to do this in math class so that when my teacher would give me a hard time about what I was doing because I wasn't paying attention, because I was bored, which, great for the math teacher to tell you all that. I was still doing mathematics, and there's actually some really amazing patterns to this, and we're going to talk about one with triangle numbers, but before I get into that, I'm going to tell you my favorite, which is just powers of 11. So 11 to the 0th power, because anything raised to the 0th power is 1. 11 to the first power is 11. 11 to the second power is 121. We know those 3. Well, it turns out 11 to the third power is 1,331. To demonstrate, calculators over here in tools. Calculator. Nope. Sorry. Anyway, calculator, which doesn't want to seem to open, which is ridiculous. $11 raised to the third power. So we'll just do 11 times 11. 11 times 11 times 11 is 1,331. And that works really well up to 11 to the 4th, because this is, if I times by 11 one more time, it's going to work out. Now it seems to fall apart in the next line, because 11 to the 5th power is not 1, 5, 1, 0, 1, 0, 5, 1. But if you think of it as place values, so this is the ones place, the tens place, the hundreds place, the thousands place, and so on, it actually works out, because we have to carry these tens over. And so 11 to the 5th power is 15016, because these two add up to make 6, 1. And so that's 11 to the 5th power. And so if you ever needed to, for some crazy reason, figure out 11 to the 20th power is really fast, you could do Pascal's Triangle and figure it out. I don't know why you need to do that, but it's cool that it's there. So Pascal's just kind of fun like that. But again, there's 1,000 patterns in here. So the first thing I want you to do is on the handout on the page, there is this, and you want to look for patterns and fill in the missing numbers. So I've shown you how to find the numbers. So to find this number here, we're going to add 7 and 21 to fill in this blank right here. And then just go ahead and fill in all the blanks. There's this pattern here. You can do this on any piece of paper. It's nice to put it in blocks and make it look clean, but any piece of paper will do, or you can open the PDF and write it in, type it up, make sure it's a different color so I can tell. It's pretty straightforward. The answer is there if you want to keep scrolling through it, but it's more fun to figure it out. What I want you to do is see if you can find any other really neat patterns in the triangle as you look at the thing as a whole. So as we go across it all the way, we can see a lot of really neat things. So if you can come up with any patterns, that'll be cool. But we're going to talk about one particular pattern today, and that's these specific ones. Find the sum of each row in Pascal's triangle is their pattern. So that means we're going to add them up so that at the sum of each row. So this is 1, this is 2, this is 4, this is 8. Remember, this number was 10, and so on. That's what it's asking you to do there, and to see if you see a pattern. Find out. I mean, what is there? And so that's what it's asking you to do there. So find the sum of each row and see if there's a pattern. So far, I have 1, 2, 4, 8. And I'm hoping if it were up to me, I'd want the next row to be 16. It's not. So, but see if you can come up with a pattern anyway. It's pretty interesting what's happening there. And so that's the first one. And just see what you can come up with. Is there a pattern? Is there not? Shade the odd numbers in Pascal's triangle. So what it's asking you to do there is shade in all of the odd numbers. So we've got our edges, which would be shaded. All the ones. That's not very exciting because they're always there. And the 3s here. 1s, 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 1s. And 5, 5, 15, 15, 35, 35. No odd numbers on that row. Odd number, odd number, odd number, odd number. And so you can kind of see an interesting pattern from here where we're making triangles with our odd numbers. And so what's really cool about this one, I think we end up with Sierpinski's, which is one I can't say. Let me actually look that up for you real fast. I can't. I don't know what it says, so never mind. Anyway, so that's what do you see? Do you see a pattern when you shade these things in? Whoops, I forgot the 7s. Over here, and the 21s. There we go. That's why it's not working. And so this is when you shaded in all the odd numbers on this triangle, what you're going to see is this thing called Sierpinski's triangle. This, and if you want to look that up and Google it, there's so many interesting things there that we're not really going to spend time talking about in this video because we're not. But that's what Sierpinski's triangle looks like as you go further out. It's basically a fractal, which means that it occurs recursively over time. And it's really, really fun to play with. But basically, if you've ever played The Legend of Zelda, you think of the Triforce, and you tessellate that Triforce over and over again, and within the Triforce, you tessellate the Triforce, and so on, you end up with Sierpinski's triangle. So, for those of you who don't know what I'm talking about, that's not really important. It's just kind of fun. But you might want to do this little search, how is Pascal's triangle related to Sierpinski's, and how that works out. It's pretty impressive that they are together and both there. So that's just something that's kind of interesting and neat in the patterns. Remember, this is my nerdvana, really, if you will. I really, really like Pascal's triangle. But the one we're going to spend some time talking about is triangular numbers. And triangular numbers are numbers that can be drawn like a triangle. For example, 3 is a triangular number because I can arrange 3 dots and turn them into a triangle. And so we've talked a lot maybe this year about square numbers, and maybe you remember them and maybe you don't, but basically perfect square numbers like 1, 4, 9, and 9, 16, etc. Numbers that are squares, and that's because we can arrange them in a square shape. When we think back into olden mathematics, they used to draw the numbers in the ground. And so they would put the dots in the ground as a triangle. So 3 is a triangular number, 6 is a triangular number. Technically 1 is, but it's 1 dot. It's not really a triangle. It's not really a square. It's one of those numbers that we just kind of let be. Find and represent the next 2 triangular numbers. So basically any numbers that can be done as a triangle. And if you'll notice, the rows of the triangle are just one more. So I need to add 4 more dots to get my next triangular number. And that's how you find them. So go ahead and figure that one out. And can you see if you can see those numbers in Pascal's triangle? what's happening with them in this triangle. So we'll go ahead and get rid of Sierpinski's triangle. And so if we just take a look at the triangular numbers, 1, 3, 6, 10, 15, 21, 28, 36, and 45. Beginning, and notice that they're on the diagonal. You can also go down this way and find them all too. It's pretty interesting that they'd be on the diagonal of this triangle. Kind of actually works out that way. And we're kind of cutting the triangle off and making another triangle, if you will. But that's where the triangular numbers are. And see if you can find any more patterns. So the powers of 11, that's the one I told you. So you can go look online and you can find it one, for those of you in Math 3, there's one related to what's called binomial expansion, which is a plus b raised to the 4th power, where you can use Pascal's triangle to help you do that quicker. That's not something the Math 1 students should be looking for. It's kind of a bit complicated. And even Math 3, that's something you'll spend more time in pre-cal talking about. But if you really like the triangle numbers, check out this extension activity. You're at point A, as you move around the grid, you're only allowed to select steps to the right or down. So you can either move right or down, and that's it. And how many steps will it take you? How many different ways can you take to get to C and A and B and so on? And is there, because you can't go like this and go back up. So there's no way to get to B except for straight across. So there's only one path to B. But there are multiple paths to C. And that's the idea, is how many paths are there to these numbers. Can you justify it? Can you figure it out? And then add another row of dots in how many different ways. So this is where so remember, this is worth 50 points. So I need you to answer all the questions on this page. And then the extension activities to get all 50 points and then fill out this whole triangle. It's just fun. Pascal's triangle is just for fun, and I hope you enjoy just playing with this mathematics. When I saw this one, I just knew I had to talk about it. So I hope you're having a good time and enjoying your last week of distance learning. Talk to you soon.